Today we're going to look at a problem similar to what you find in section 3.5, which is graphing rational functions. Our function today, h of x equals x squared plus 3 over x minus 1. We do all the same things that we do when graphing a polynomial function in terms of looking for where the first and second derivative is positive and negative. We're looking for changes in sign, but we're going to add vertical, horizontal, or oblique asymptotes to this situation. So we'll start by finding the first derivative. We'll use our quotient rule. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. And when we simplify the numerator, we end up with x squared minus 2x minus 3 divided by x minus 1 squared. We're going to find the critical numbers, which are where the derivative equals 0, which is the numerator, or the derivative does not exist, which is where the denominator would equal 0. The numerator factors to x minus 3 and x plus 1. So at negative 1 and 3, the derivative equals 0. And we see if we substitute 1 into the denominator would equal 0. The numerator would not. So that is also it does not exist. So there are our critical numbers. Now we're going to take the first derivative and then find the second derivative. So again, we have the denominator times the derivative of the numerator, which would be 2x minus 2. Didn't leave myself a lot of room here. Minus the numerator, derivative of the denominator using the chain rule, 2 times x minus 1, all divided by the denominator squared. So that's going to end up being to the 4th power. And we're going to simplify our numerator. We would factor out an x minus 1, and we'd be left with an x minus 1 times a 2x minus 2 minus, and then we'd have a 2 times x squared minus 2x minus 3. Notice we have an x minus 1 and an x minus 1 to the 4th in the denominator, so that would divide out to x minus 1 to the 3rd. And when we simplify the numerator, all of that will end up simplifying to the constant 8. And we end up with, and again, that would go to the 3rd, x minus 1 to the 3rd power. So looking for places where the second derivative would equal 0, since the numerator is a constant, it would never equal 0, but the second derivative at 1 also would not exist. So we've now found all of the places where the first and second derivative equals 0 or does not exist. So we will do, I'll do a interval chart here, a sign chart rather than number lines, which we've done in the past few. So just so people can see something different. So we have our intervals. We will look for the sign of the first derivative, the sign of the second derivative, and then make our conclusions. So we're going to use negative 1, 1, and 3 for our intervals, so we have to be less than negative 1. We're going to go from smallest to largest, equals negative 1. Then we'll be between negative 1 and 1, since that's our next value, at 1. Between 1 and 3, at 3, and then values greater than 3. So looking at our first derivative, and always easiest when we're in factored form. And again, we're looking for the sign. And notice our denominator is a binomial squared, so any value we substitute into the denominator will be a positive number, so we don't really have to concern ourselves with the sign there. Here, the numerator, we could plug numbers into our factors, but you also should notice that you have a quadratic, which is a parabola. It has a positive leading coefficient, which means it's face up. So our zeros would be -1 and 3. So if we were to just sketch here, that graph would look something like that. Vertex would be over there, but all we're concerned with is the sign. So we know that in our parabola we would be positive, 0, negative, 0, positive. So pretty easy to go down. And then, so we are positive, we are 0, we are negative. Now remember, at 1 it does not exist because it would make the denominator 0. Between 1 and 3 we're still negative. We're 0 at 3, and then we're positive, and we'll write our conclusions here in a minute. For the second derivative, the numerator is always positive. It's a constant 8. So we're just looking here, and we have this cubic, x minus 1 to the third power. Any number less than 1, the binomial, or this inside would be negative, cubing would be negative. So we are negative at 1. Does not exist, and then beyond, any value substituted into the second derivative would be positive. All right, so now we're going to make our conclusions. In this interval, since the first derivative is positive, the function is increasing, and because the second derivative is negative, the graph is concave down. Here the graph is still concave down because we are still second derivative is still negative. Notice we have a 0 here for the first derivative, and we look after, it is negative. So f is decreasing. And because our first derivative changes from positive to negative, at -1, we would have a relative max. We have does not exist here for the first and second derivative at 1. After 1, first derivative is negative, second derivative is positive, so f is decreasing still. And the graph now is concave up. Notice we do have a change in concavity on either side of 1, but if we go back to the original equation, notice if we substitute 1 in, the numerator would be 4, the denominator would be 0. So 1 is not in the domain of the function, and that also tells us because we get a non-zero number divided by 0, that would be a vertical asymptote. So there is no point of inflection because that value 1 does not exist. It's not in the domain of the function. Again, the first derivative is 0, so we're looking at what happens on the other side of that. So since the first derivative is positive, f is increasing. And all of these, for all of this interval, the graph remains concave up due to the second derivative being positive. And so here, a first derivative changes from negative to positive. Therefore, at 3, we have a relative minimum. All right, so this sign chart is going to give us all the things that we need to graph in the sense of concavity and direction. But again, because we have a rational function, we need to look at vertical asymptotes and the end behavior. So we're done with this piece of paper. We're going to turn to a new sheet. And our function, again, h of x equals x squared plus 3 over x minus 1. And h of 1, rather, would be 4 over 0. Therefore, we have a vertical asymptote at x equals 1. And the end behavior, we notice that the degree of the numerator is 1 greater than the denominator. Being greater in general means that the function will go off to positive and negative infinity as x goes to positive and negative infinity. But the 1 greater tells us that we have a slant or oblique asymptote. And we find that by doing long division here, or we could do synthetic division since the degree of the divisor here is 1. But I'll do long division just to practice that. X squared, we need a 0x placeholder. And x divides into x squared x times. We multiply times the divisor, subtract, use our parentheses to help us keep track of signs. That becomes a positive x. Bring down the 3 since we have two terms. That becomes a plus 1. Again, we subtract. Our remainder is 4. And so this tells us that we have a slant or oblique asymptote at y equals x plus 1. So we'll sketch a graph here, and I'm sure you would be putting this on a piece of graph paper so that you are much more accurate than what I am going to do here on binder paper, but you'll get the idea. So let's see, we have a vertical asymptote at y equals 1, or rather x equals 1. We have an oblique or slant asymptote here at y equals x plus 1. And you may recall from here that we have a relative max at x equals -1, a relative min at x equals 3. So we're going to want to know those function values, and h of -1 was, or is -2, h of 3 is equal to 6. Easy to find the y-intercept as well if I substitute 0 for x. We'll get -3, so not a bad idea to have that point. So again, at -1, which would be where the slant asymptote intersects the x-axis, we have a y value of -2. That's a relative max. We have a vertical asymptote at -3. At the value 3, we have a y value of 6. Extend that up. And so again, looking at our conclusions, when x is less than 1, we're going to be increasing a max at -1 and then decreasing graph concave down. So here we are from the asymptote increasing, we're concave down. There's our max through the y-intercept. Now it's decreasing and again approaching asymptotes. And here after 1, decreasing, a minimum at 3, increasing, graph always concave up. So here we are from the asymptote decreasing, concave up. There's our min. And there's our graph. And those of you who had Miss Trent would draw better arrows at the end for the one-sided. But here is your graph for your rational function.